Introduction to Microelectronics, problem 4.7. The channel length of a silicon gate NMOS transistor is the spacing between the source and drain diffusions, and the spacing is currently 3 micrometers on the masking oxide used to make the transistor. So this length is 3 micrometers. The source and drain junctions are diffused to a depth of 0.5 micrometers, right? So we have a junction depth of 0.5 micrometers. This is 3 micrometers. Using a constant source diffusion, the surface concentration N naught is 1 times 10 to the 20th. Okay. And the wafer has a concentration of N is equal to 1 times 10 to the 16th per centimeter cubed. And we're asked to find the channel length after the diffusion is completed. And why will the channel length not just be 3 micrometers? Because, as we can see here, when diffusion occurs, it not only goes vertically down, it will also go and diffuse into the surface laterally, which is why the gate length will be less than 3 micrometers. By how much? We'll see. To find out the exact numbers, we use the following figure. Figure 4.10. This figure relates the lateral to the vertical depth based on the differences in concentration. For example, if the concentration for N over N naught is, let's say, let's say it's 0.5, which in that case the concentration on the surface is just 2 times. So just barely diffusing more. If you follow that line, what's going to happen is, if you follow it vertically and then you follow it horizontally, you get the following value of approximately, 0.1 over 0.5. So that's approximately 0.2. What this gives you, this value 0.2, is the depth that is actually diffused laterally. Okay? So this chart actually shows you the lateral diffusion depth. If you multiply that by the vertical diffusion depth, you get the actual lateral diffusion. So in this example, we get L lateral. Let's say we're still diffusing to 0.5 micrometers. We get 0.2 times 0.5 is equal to 0.1 micrometers. So in that case, if we have 3 initially, we would subtract, right? So we have 3 initially, and we diffuse 0.1, we diffuse 0.1, we end up with 3 minus 2 times 0.1 is equal to 2.8 micrometers. Cool. Let's do that again and repeat the same process for our actual values. And I encourage you to try doing this yourself first, and then I'll show you how to solve it. Cool. So we have N over N naught is equal to 1 times 10 to the 16th over 1 times 10 to the 20th, which is equal to 0.0001. So we have a constant source diffusion, so we use this one, right? We use this graph, and we follow this line right here, and then this line corresponds to a lateral. Sorry, I don't know if I can do this. That's fine. Let's draw a more straight line. There we go. Not super clear, but good enough. Corresponds to a lateral depth of 2.3 and a vertical depth of 2.8. So the length laterally that we actually diffuse is 2.3 over 2.8. The ratio times 0.5, which is the junction depth, to get 0.41 micrometers. So L is equal to 3 micrometers minus 2 times 0.41 is equal to 2.18 micrometers, I think. This is not a hard problem, but it is important conceptually to understand it. And it is important to understand how diffusion can occur into lateral directions and isn't perfectly anisotropic. So it's not perfectly vertical. There are horizontal components to it. Thank you.